Welcome everyone to EuroSciPy 2023, the first ever tutorial on a Monday morning at 8:30 a.m. Thank you for showing up. And this room is for network analysis made simple and fast. If you're looking for another one, this is not the right room. And my name is Mridul Seth. I'm a code developer of a package called NetworkX, and we will be using this package today to do network science, graph theory. And if you thought that, and when I say by graphs, I mean like graphs, nodes and edges, not pandas.plot. That's a different graph. And we will be using Jupyter notebooks today to follow along the tutorial. So if you go to this URL, mriduls.github.io/nams-lite, it will take you to a Jupyter Lite instance. So what Jupyter Lite is, it's magic. You don't need to install anything. Everything is in the browser. It's WebAssembly, cool things, and very, very magical. And like you don't even need to worry about environments or anything. It's everything is in the browser. So the initial load may take some time because it's depends on your internet connection. It's like a 50 MB load. But after that, you don't even need internet. So please go to that link, and it would look something like this when you open it up. It's your Jupyter lab interface. And if you have any questions, if you have any doubts, if you have any anything, please stop me and ask the question. And you need a mic to ask the question, so it goes into the recording. And because this is a talk, this is not a talk, this is a tutorial. So, I'll get bored talking for 90 minutes. So please, stop me if you have any ideas, any questions, please let me know. And in this tutorial, we will try to cover these topics. So just a very very basic introduction to graphs, networks, what they are, and how to use the NetworkX API to model them. The second one would be some basic visualization, and we'll try to cover a very brief overview of what are hubs, finding important nodes in a network. And the third part would be dispatching with GraphBLAS, and that's the fast bit. And for dispatching, we will use another notebook. We'll worry about that later. And all of this material, if this is available on this link right below. You can just Google that, network analysis made simple, that should show up. And that has enough material for 8 hours of tutorial. So if you want to set for 8 hours, we can do that, but let's not. And so before we start, just with your hands, I do want to know about how many people have heard about NetworkX before. Cool, nice. How many of you have used NetworkX before? All right. How many of you have studied graph theory in school or just for fun, as one does? See, yeah. And how many of you are comfortable with Python, for loops, list comprehensions, classes? This is something that you understand. Good. And how many of you have experience with pandas, matplotlib, numpy? Perfect. And also, how many of you have experience with Jupyter, working with Jupyter interface, command enter, you run a cell? Perfect. All right, so let's jump in. So does everyone here have this screen ready? If you do not have, please let me know. This is the link for that. Oops. This is the URL for that. If you do not have it, and if you want to have it, please raise your hand. All right. So everyone's here? Perfect. Thank you. So just some logistics. So you have a bunch of notebooks here. So we'll go through them one by one. And again, if you have any questions, any ideas, please shout them out. And yeah, so 8:36 Monday morning. Let's write some Python. And so if you open the first notebook, it's called 02 Prereqs. prerequisites. And the idea here is to just some warm up of because a lot of, at least in NetworkX, a lot of things that we will do is dictionaries, list comprehensions, and manipulating data frames. So there's just a warm up. So the first exercise is, given the following line of code, this S for S in my favorite things, what are the plausible data structures for S and my favorite things? And just think about it for a bit, and then we can have the mic around, and you can shout out your answers. You don't need to shout, it's a mic. Any ideas? What could be S? Any ideas? All right, so S could be a dictionary. We have one answer. Any other thing? What could be S? Yeah. String. It may not be a string, because if you look at this, the if condition, so you need to access something. So yeah, so dictionary is the usual suspect here. But what you can say is that anything that has a get item dunder implemented could be S. What about my favorite things? What could that be? Yeah. Oh yeah. Oh yeah. So please maybe raise your hand, and so we can get a mic running towards you. Yes.
The most obvious is a list.
Yes, the most obvious is a list, because you see that for S and my favorite things. So you're iterating through something, right? And at least in this, we can say that yes, for S, and my favorite thing is a list, or just any container you can iterate through. And and also this is a coding heavy tutorial. So if you are thinking you'll just sit here and relax on a Monday morning, I'm sorry. So the next exercise is, you have a list of dictionaries. So if you see these names, you have a list of dictionaries, and also the other thing is that the first time you run your kernel, it will take some time to set up things in the backend. But yeah, so the first exercise is that you have to write a function that takes in this names list of dictionaries, and it returns the dictionaries in which the surname value matches some query. So this would be something like how it would look like: find persons with surname. You pass in a list of dictionaries, and you pass in the query. And if you're done, you can also test the implementation in the last cell. The asserts should pass. Anyone done with the function? Yep. Perfect. So we'll move forward, and once this is done, Let's jump to the third notebook, and this is about like the takeaways from this tutorial. So we have like two broad goals. The first is a technical takeaway, which is basically understanding how to model your graph data. And if you have never seen graph data in real life, or like at your work or in your studies, you're missing out. Like in my opinion, anything that if you try hard enough, anything can be a graph. So the first technical takeaway is that understanding how to model your data. Like once you have your data, how to extract things out of it. So which basically follows the NetworkX API and how it works. And the bigger goal would be the intellectual goal, and that is how you think about relationships between data. And I do not mean RDBMS. I just mean usually when you have a bunch of data points, they may or may not have some sort of relationship between them. So just trying to think in a graph way. That's the idea behind this workshop. And let's jump to the fourth notebook. It's called Graphs, and let's start with a formal definition of networks. So, how many of you had done graph theory before? Can we have the show of hands again? All right. So, if all of this thing does not make any sense to you or looks too intimidating, it's fine. You don't need to know any of this. So usually graphs in maths are represented as a structure which has two sets. One is a node set, and the other is an edge set. A node set is a set of nodes, and nodes are entities in a network. So we're going to see later how it looks like. Maybe that will make it make more sense. And an edge set is a set of relationships between those entities. So you always have this node set and edge set. And the term set here is important because in a set, just like a Python set, all values have to be unique, and there is no set of order. So for example, in a pandas data frame, you can do .head. It will give you the first 5 data points, which may or may not mean something. If it's a time series, it will give you the first 5 data points in that time series. So it has a sense of order in it. But that's a very hard thing to do for graphs. There's no such, when you say this is a graph, give me the head of the graph. There's no such thing as a head of a graph. It's an unordered abstraction. So that's just something to keep in mind. And so let's try to think of examples. Do people have any examples of networks? In real life, you're walking along the streets. What do you think about when you think of networks? Any examples people can think of?
So a good example would be the metro stops, right?
Sorry? Yeah, metro stops, yeah. So transportation networks is a big thing. And how metros, how the metros are scheduled, and also you can make it a multimodal network now, how buses are scheduled, and how how you can walk between them, how you can bike between them. So everything is a network. Any other ideas? When you open your phone, you open certain things. Any other ideas? What is a network? What could be a real world example of a network?
Our connections on social media to friends. So that's
all social media, right? Facebook, Twitter, and I'm not sure. Is TikTok a network? That's a good question. I'm not sure because I've never used TikTok. But but like wherever you have this sense of like, we are following each other, or there are any sort of relationships between two entities, then we can model that as a network. This is used not just in fun things like social media, like biology, like when you're doing protein interaction, so there's this big thing of protein interaction networks, how different proteins interact, and then you have transportation networks. So as I said, if you try hard enough, anything is a network. And moving to another theory bit is types of graphs or network. And all through the tutorial, I'll use the term graphs and networks interchangeably. So graph comes from graph theory. If you are like, a pure mathematician, that's what you would do. Network comes from network science. It's like if you want to be a hipster data scientist, that's what you will use. So, types of graph there are lots of types of graph, but like in a very very basic inherent essence, there are two. One is a directed network, and the other one is an undirected network. So for a directed network, an example would be Twitter, because or the other, or X, I'm sorry. Or like if I follow someone, that does not necessarily mean they follow me back. But for example, in the case of Facebook, if I'm friends with someone, that also means that they are friends with me, at least on Facebook, right? So there's this, that's the notion of undirected and directed. For example, a flight network, if you model all the flights of all around the world, is that a directed or an undirected network? Undirected is one of the answers, and you would expect it to be an undirected network, but it's not really an undirected network, because just because there's a flight from A to B, that does not necessarily mean that there's a flight from B to A. There should be, but that does not. There's no guarantee that it would be. So for example, a flight network is a directed network, and so just like think of more examples like this. And that's I would end this notebook with edges are the interesting bit of a graph, because like a node itself is a data point in itself, and like if you have all the information for the nodes, you can just put them into a data frame and end. Just like you can analyze that. But as soon as you move into graph theory and network science, like that's the one that holds all the information of like how different data points are interacting with each other. So edges is the heart of the network, and I hope I have given you a nice pitch of why you should do these things. And let's jump to NetworkX intro. This is the 5th notebook, and if anyone who joined later wants to follow along, this is the link for that. Does anyone want to see this link, or anyone has? Okay, please. Just go to this link, and this link will take you to something like this. All right, so. And again, like if you have any questions, any ideas, please feel free to stop me in the middle. And this is not working. like do the cells work for people? Like if you try to execute them, okay, so it's just me, obviously. And yeah, but anyway, so in the 5th notebook, what we'll do is we'll just start with the basics of the NetworkX API of, once you have your data somewhere sitting on your disk in a CSV file or something, what do I do with that, right? So we are going to work with the data model. Wait, I'm going to do something nice. there are a lot of quirks of Jupyter Lite. So one of the quirks is that if you open it in incognito mode, it will not work. I mean, it will work, but you cannot access another file inside Jupyter Lab in incognito mode, at least in Firefox. So fun stuff. But anyway, as it works now, so that's good. But let's jump back. So you'll see something called like Micropip. You don't need to worry about this, and make sure you're running each cell. Otherwise, notebooks, it won't work. So is everyone on the 5th notebook? Is anyone stuck? Any questions? Please shout it out, or we can get a mic to you. All good? All good? All right. So Micropip is a technical detail for Jupyter Lite. So don't worry about that. So yeah. So for the last 20 minutes, I was trying to lure you into everything is a graph. Please think in a graph way, and let's see how we can do that with code now. So one of the reasons I like NetworkX, not just because I'm a code dev, but is that I really like the API. It just makes sense, at least to me, and to be honest, to a lot of people. NetworkX has a lot of issues in the sense that it's a pure Python library, so it's mainly performance issues. It's a pure Python library, so if you are into a billion edges, please don't use that unless you have access to some supercomputer with 1 terabyte of RAM, and even then, please don't use this. There are much better ways of analyzing a billion edges, but even with these shortcomings, people do keep on coming back to NetworkX because the API is very friendly, at least that's my opinion. It's a subjective thing, but that's my opinion. So, for example, if you want to create a graph, this is how you would usually write this. And just like with import NumPy, we usually do import NumPy as NP, we do import pandas as PD. With NetworkX, we do import NetworkX as NX. You can do it any other thing that you want to. So usually we create a graph with something like g equals nx.graph. So you have this empty graph object, and to access a node, you would do like g.nodes.node, and you would see that this is very similar to the dictionary access methods, and that's because underneath NetworkX, it's all dictionaries. So it's dictionary of a dictionary of a dictionary of a dictionary. You would see that later. But just like that, you can also access an edge by passing in the 2 nodes. And so let's move on to some writing some code and running some code. So let's do our imports, and we are going to import this extremely important data set called the 7th grader network. It's a very controversial one, and I'll explain you why. So what you do is you go to a class just like this, but of 7th graders, and you ask every student, who do you want to play basketball with, or who do you want to go painting with, or who do you want to go for a run with? So you basically ask them these 3 different activities, and they tell you who they pick. And the controversial part of this is that, let's say I pick A. It's a directed network. It's possible that I want to play basketball with person A. They don't want to play basketball with me, right? So a lot of fights happened because of this data set collection. I don't know if that happened. I'm just making stuff up. But yeah, so let's see. As I mentioned, I can pick A as my favorite person, but that does not mean that I am A's favorite person. And that's why it's a directed network. And also, if you want to actually look at what this load 7th grader network is doing, you can go to the utils.py, and it has all of these util functions that we're using. So read a CSV file, clean it up, add it into a network, and return that network. But yeah, so the type of G is a directed graph because I like A, the person does not like me back. And if it were a graph, this is what you would graph. This is what you would get. NetworkX.classes graph.graph, and what we can do is we can query nodes. So every student here has their name as an integer. We don't actually put their actual names in this data set because I guess privacy. And so if you do g.nodes, and this is the API bit I'm talking about. So how do you get the nodes? You do g.nodes, you get the nodes. So you would get something as node view. Forget about node view, you don't need to worry about that. So, and as I said that, there's no such thing as the first 5 nodes. So if I try to do this, you would get an error, and it has nothing to do with that order, but it's just because the node view object that we got, it does not support slicing. So what you need to do is you need to cast to list, and you get this. So, and the only reason you would do something like this is, like the slicing bit is just, let's say you have 10,000 nodes. You don't want to print all of that and just mess up your Jupyter notebook. So just print any 5 nodes. So I was trying to push for something like sample. So instead of getting the first 5 or the last 5, let's just add a new function in NetworkX, which is a sample of nodes from this graph. We haven't done it yet, but hopefully soon, sometime we'll get there. And if we do length of g.nodes, it will basically tell us how many nodes are there in the graph. And as you remember, the nodes are students. So in this 7th grade class, we have 29 students. And so this is the other fun bit about NetworkX, is that because it's dictionaries all the way down, you can kind of just put anything inside it. So anything that is hashable, and if the word hashable does not make any meaning, it doesn't hold any meaning to you, don't worry, forget about it. But anything that is hashable can be a node, first of all, and that thing can also be a node attribute. So let's say we are in a class of humans, and a node attribute could be what's their date of birth, where do they live, what are their food preferences. So this is more information about the node itself. In the case of a transportation network, it would be what is the latitude, what is the longitude, what is the opening time, what is the closing time of that metro station. So you can basically keep on adding this information in a network, and dictionaries are a good way of storing all of this information. So, and just like for nodes, we can also do this for edges, but we'll see that a bit later. So in this case, their gender is represented in the, when you do data equals true, it basically gives you all the data that has been shoved into the graph. So we have student A, and we have the gender there, and just a subset of it. And just like that, we can also select out nodes. So if we do that just g.nodes, it will give you this node view. But let's say I want to know the information about student 11. I can pass in this, and I get information about student 11. That's not their name, that's just the anonymous name. And it's important, at least in the NetworkX context, to remember that all of these are dictionaries. So just how you would treat a dictionary while you're iterating through it, it's you usually do for key, comma, value in dictionary.items, and then you do things with key and value, right? So just like that, you can do with g.nodes. The g.nodes, it gives you a dictionary-like thing, which is basically for n, comma, d, which is the node, comma, the data attributes in g.nodes data equals true. You can just do your things, what you want to do with the node and the data. So in the interest of time, we will not actually do this thing. There are a bunch of exercises in this, and as I said, if we go through all of it, it will take a lot of time. So in the interest of time, I'll skip some exercises, but let's jump to this thing now. So just like nodes, we have edges. So if we do g.edges, it will give us this whole screen of numbers. Like these are all of the relationships between them. So what it tells you right now is that there was some activity that one chose 2 for. There was some activity that one chose 3 for. And so, for example, if you go to ask if you go ask 1, who do you want to play basketball with? That person say 2 is fine, 3 is fine, 4 is fine. And for 5, 6, 7, maybe they chose another activity. So this is how the data was constructed. So just like g.nodes, if you want to just get a small sample of it, let's just get some 10 edges, we can do something like this. And like the cheat code for NetworkX is that whenever you're stuck in some slicing error, always cast it to a list. I mean, it's not just a NetworkX thing. If you're ever stuck in Python, just cast it to a list. It will fix everything in your life and in your code. So let's, just like g.nodes, we do g.edges. So if you find the length of g.edges, it gives you 376. That means that there are 376 connections between all of these 29 kids. And just like nodes, even edge itself can have a lot of data. So in this case, we have the data count, which means that, for example, in this example, if you look at the last one, 1, 6 count equals 3. What this means is that like the student 1 chose student 6 for all of their 3 activities. So maybe 1 and 6 are besties. I don't know. We can analyze this data and find out who are besties. So, and for example, I'm just trying to show you all the different ways of accessing data inside NetworkX. So if we pass in g.edges, you get this monstrous thing, right? So if we do for example, 1, 2, it will give you all the data attributes, and we can basically keep on adding things. And this is a dictionary, so we can just keep on adding new key value pairs. Going back to our old examples, like for the transportation network, what could be the edge attribute? Maybe the fare, or if you're going from metro station A to metro station B, this is your fare. If you're going from, I'm just trying to think something, but the basic idea is that you can basically put a lot of things inside that node and edges. And if you try to access something that does not exist, so node 15 and 16, so there's no edge between 15 and 16. So student 15 never chose student 16 for anything. And so you basically get an error. And just like node views, we can iterate through all of this. So usually when you would try to get data out of a graph in NetworkX, what you would do is for n1, n2, d, and g.edges, data is equal to, and n1 is your first node, n2 is your second node, and d is the data, the metadata dictionary between them. And again, we'll skip this exercise. So we saw very basics of the NetworkX API, how to access nodes. But once you have added access node, what if you want to change the nodes? So you had this data that you read from a CSV file. Now there's a new student who joined this class. You want to add more data to this graph, right? So, and this is the API I'm talking about. How do you add a node? You do g.addNode, and you pass in the node name you want them. So let's say the new student name is 30. So you'll pass in that node name. We can basically pass in any key value pair as the node attributes. And just like add node, we can do g.addEdge, and node 1, node 2, followed by a bunch of key value pairs. So in this exercise, what we were supposed to do is we add 2 students, 30 and 31, and they are new students. They just joined the school, so they basically just hang out with each other. So the idea was to just and there's also, if you go back home and you want to do this exercises, you can look into solutions to actually get the solutions. So, but going back, and with this notebook, it was just to show you how very basic things, like add nodes, how to access nodes. You can also remove nodes. It's just remove node, and you can read all of this on our API documentation page, and just some coding patterns. And it's not just for NetworkX. It's just Python in general. Is that if you can make things with list comprehension, make them. They're easier to read. They're nicer to work with, and at least in the context of NetworkX, you would need a lot of list comprehension, especially when you are trying to extract data out, because you always need to go in to the dictionary and you need to get the data out. So that's something just to think about. And again, if you want to read more about the NetworkX API documentation in general, just please go to our docs. I like to think we have good docs. Please prove me wrong if we have bad docs. And also, this is a fun exercise that you can do when you go back home today or after the conference, is unrequited friendships. In this, what you have to find is, you have to find relationships where A chose B for some activity and B never chose A. So, it's a one-sided friendship, as they say. But let's jump to the next notebook. It's called the Viz one. So, and please feel free to interrupt me if you have any questions, if I'm going too fast. I know I'm going too fast, but no, all right. So the other main thing of graph theory and network science in general is just visualization, because it's hard, and I'll show you why. So just like the last notebook, we load this data set again, the load, like the 7th grader network, and we plot it. So NetworkX has some inbuilt plotting functionality, and you get this out. Can anyone make anything out of this? Can you infer anything just by looking at this image? Nope. See. And you cannot, because there's a technical term for it. It's called a hairball. And this happens a lot with especially dense graphs, because you can come up with some some way of laying out the nodes in such a way that this makes some sense, but that's a very, very hard problem. It's like an active research area. There's full conferences just devoted to graph drawing. So it's a hard problem. And usually you always need to think about the context of the data. For example, in a transportation network, it's easy. It's easy because you already know how to lay out the nodes. So because every metro station would have a latitude and a longitude. And so it's easier in that sense that you know how to lay out the things, and even the edges between them will make sense. For example, if on a straight street, you will never create an edge which goes as a curved edge, right? You'll always make it a straight edge, because that's how the train will travel, the metro will travel. And the idea here is can we come up with a visualization that gives us some information just by looking at it? It doesn't need to give us quantitative information, just qualitative. Interestingly enough, I was talking to someone who works in a social sciences institute in France, and they were a software engineer, and they were working with a bunch of social scientists, and they told them that the person told me that they have to come up with these pretty looking images, because apparently a lot of social scientists like to come up with qualitative inferences rather than quantitative. They don't want to run statistics, they want to look at an image, and this is what's this is what you can infer out of that. So let's try to make prettier images. That's what this notebook is for. So we can get some information. So yes, we know that this graph is directed. Good. So let's say we try to plot the same thing, but with a bit more information. So in this case, I'm not sure, I think it's visible, right? So in this case, we just add the node label name, which is like the student name on the node itself. So now just by adding this little bit of information, we do have some more, like, we can get something out of it. So for example, 29 and 28, they seem to have chosen each other for some activity. So we get a bit more out of it just by looking at the image that came out. So the other fun way of doing this is something called a matrix plot, and this will make a lot of sense because so graphs, like the one that we just saw, this thing, they can very easily be translated into matrices. So there's a one-to-one mapping between a graph and a matrix. And if you plot that matrix in a fancy way, it's like wherever you see this dot, that's just a 1. That is what it is. So instead of like having a NumPy matrix, which is like 1, 0, 0, 1, 1, 1, this is what you get. It's just like, it looks prettier. But just by looking at this, we can kind of infer certain things. Does anyone want to infer anything? Any ideas? Just by looking at this. Like, you need to see where there are dots, where there are no dots. Just to explain this again, this is a matrix. So these are nodes, like 1 to 29. These are the same nodes, 1 to 29. And if they're an edge between, for example, 1, 6, so let's say this was 1 and 6, you have a dot here. So this is how the matrix is drawn. And it gives you one very nice information which you don't actually see here, which you could if you looked hard, but it's much easier to see here. Yeah. So like just for the recording, like they mentioned that the diagonal is empty here. So if you look at right here, so no one said that who do you want to play basketball with? They didn't say myself. So what that means is that there are no narcissists in this class. So that's good. So there's good future for this bunch of students, I guess. So like something like this, you could kind of figure that out, that there are no self loops. But as soon as you went into this, like, hairball of a mess, it would be even hard to get that information out. And you can also, like, maybe try to claim something about the density of, like, edges between this group and this group, or like, So let's say this was a much more complicated graph with a lot more like categories. Then you can look at, like densities between different clusters and try to, come up with some inferences. And just like that, we have something called the arc plot. I'll just plot them out first. So what this tells you is that any ideas what can we infer from this? These are just nodes. Like all the nodes are just lined up in one line, but with like according to their category. Can we infer anything from this?
Can I ask, in this one, the directionality is not?
Yeah, it's not included. That's a good catch. But like in this plot, there's no sense of direction, and it loses out on that information. But you like maybe this graph is not a good example for that. But in a lot of graphs, what you would have is you would have these localized clusters between categories. So even if you lose out direction in that, you would get that information out. So it's like the idea, what I'm trying to convey here is that it matters a lot how you lay out your nodes, especially if you're not in the matrix realm. So and Circos plot is just arc plot, but you just make a circle out of it. So for example, if you had a very clean donut-like thing, that would mean something like there are not a lot of intergroup connections. So there are a lot of intragroup connections, but they're not intergroup connections. And this is one of my favorite plots. This is called the Hive plot, and you would use something like this when you want to look for intergroup connections versus intragroup connections. So what you have right here between these two is how nodes are connected inside that same group. And this is how nodes are connecting across groups. So for example, if there was no friendships between male and female, then this would literally be empty. So there would be no edge between them. So if for example, if we try to make this Hive plot out of Facebook network, which would be impossible, but still, if let's say we can, then what you would see is that you would see these maybe localized country, these bits of countries which are very connected inside. It's very easy to know for me an Indian rather than knowing a Swiss person, right? So on Facebook at least. So you would have these very dense intra-group connections and very sparse inter-group connections. So, and again, this is something that would be very hard to get from this. So, yep.
And in these Hive plots, what does define the ordering within one group? So if you, for example, look in the female,
Yeah.
if they're aligned along a line, what defines who's first and who's the next?
Yeah. So the question was that what defines the order between how these are set. There's no order, at least inside intergroup. You can add an order, but you don't need to add an order between inside that group itself. You can add order if you want to, if you think that gives you a bit more information. But by default, there's no order, and so if you go back to the first notebook, we said that edges have the most information, which is good. But in my opinion, when you're drawing, nodes are the most important bits. If you can figure out how to lay out the nodes, then you can. Because if you look at least not in the matrix plot, but in all the other plots, that is the hardest bit. How to lay out the node that the resulting graph makes some sense. All right, so let's jump up to the 7th notebook. It's called hubs. So till now we were just we read our data from disk, we plot the data, made some inferences, made some pretty pictures. But what if your boss comes up to you and asks you for give me some real statistics? I don't just want a dashboard, I want numbers, right? So for that, we'll open the 7th notebook. It's called hubs, and in this we'll use an example of contact tracing. So it was pretty important. I mean, it still is important because of disease spread. And in this we have an interesting data set. It's called the socio-patterns data set. And how they created this data set was that they went to a conference or a art exhibition, I think, and they gave a beeper to everyone. Imagine this thing with basically it can figure out who it's near to. So everyone gets a badge with a beeper, and if you talk to, you don't even need to talk. If you're basically standing next to a person for 20 seconds, you get a connection. That doesn't mean anything, but you get a connection out of it. So this is how they basically ended up creating the network. That if two people are standing next to each other for 20 seconds, they may have met, and that means that there's an edge between them. So this is how the graph is created. Any guesses what would be the type of the graph? Would it be a directed graph or an undirected graph? In a conference, you make connections. Are they directed or undirected? Just shout it out. Well, it's an undirected graph because it's fine if I'm the only one doing the talking, you're still there. So it's still an undirected graph. I mean, you can argue that if it's a monologue, then no, there's no connection being made. You can argue that, but at least for this data set, if you're just listening to someone, you are an edge for them. And let's see how big is the graph. So we have 410 nodes that 410 participants showed up at this conference, and they made 2,700 connections. So maybe if you're organizing a conference, maybe your aim should be how to increase the number of connections. Maybe that should be that is how we should measure like how successful is a conference. And so if I ask you, how would you define who's an important person in a conference? Let's forget about network science. Who's an important person at a conference? Any ideas?
The one with the most connections?
No, forget. We don't know anything about network science. Organizer, right? So one of the organizers are important, right? Anyone else? Keynotes. So yeah, organizers, keynotes. So let's bring back the last 1 hour of all the cool things that we have learned about network science. In the context of this network data, so would organizers or keynote have a high number of connections or edges, or yes, no? Yes, I see a lot of shaking heads. So yes, and the technical term for that is neighbors, at least in graphs, is that a node is, if a node is connected to any other node, like that node is a neighbor of that node. So one very simple way of usually finding importance is just count the number of neighbors. So if for example, an organizer would be someone who's maybe talking to everyone, trying to make sure everything is working, right? It's a hard job. So they would be talking to everyone. So they would have a high number of neighbors, and that is probably true for keynotes too. People want to go and talk to them. Maybe it's just monologues, but it's still, at least with this definition, if you stand in the vicinity of a keynote speaker, you are their edge, so you are their neighbor. And but there's one important bit. There's no right definition of importance in a network. So context is very important. So it depends. So this is just one of the ways of finding importance. For example, in Twitter, who is the most important person on X? I'm sorry, X, or any social network. One usual way of finding that out is who has the most number of followers, which is basically neighbors of that node. But that does not tell you the whole story, and we'll look at that later. So in NetworkX, we have something called g.neighbors, and if you put the node name, and again, just like last example, all the nodes here are integers. They don't need to be integers. They can be anything. They can be strings. They can be tuples. They can be another graph itself. So a NetworkX graph can be a node in another NetworkX graph. So it can be an MP3 file, which is assuming the class is hashable. So it can be anything, and that's the beauty here. But yeah, so g.neighbors.7, it gives you this weird-looking thing, dict key iterator. If you've never seen this, as I mentioned before, this fixes everything in life. So just cast it to list, and it will give you all of these nodes. So 5, 6, 21. So presumably the person 7 met all of these other people when they were at the conference/exhibition, and let's just try to find what's the length of this. So person 7 met 7 people. That's by accident, but yeah. So the person 7 met 7 people, and again, in the interest of time, let's not do this exercise. But the exercise is to find the find the node which has the highest number of neighbors. So basically finding the most important node that we just discussed, but we basically look at every node in the graph and count the number of neighbors they have, like length of list of g.neighbors to 10, and we do that. And you would see that you don't actually need to we do this exercise usually, but there's an inbuilt function in NetworkX to do it. So you don't actually need to do the exercise, but you should. But yeah, so generalizing neighbors to an arbitrary size graph. So this is important when we are comparing two different graphs. So let's say we have two conferences, EuroSciPy, EuroPython. You go to EuroSciPy, you say that the most important node had, 80 neighbors. You go to EuroPython and you say the most important node has 70 neighbors. Can you compare them? The answer is no. And the reason behind that is that you need to make sure that, context. So if, for example, at EuroSciPy there are 300 people, and if at EuroPython there are like 400 people, you can't just randomly compare numbers between them, but what you can compare is a ratio. For example, if a person met 20% of all the attendees of a conference versus a person met 18%, so you have something to compare it with. And because we like fancy names, we people came up with something called degree centrality. And what the word degree means the number of neighbors. So in our previous example with node 7, the degree of node 7 would be 7 because it has 7 neighbors. And this centrality is basically when you normalize it with the total number of neighbors. And quick question, in a graph of n nodes, how many neighbors can you have? Yeah, so n minus 1 is the usual answer for simple graphs, but what if you're allowed to be your own neighbor? Then it's n. But yeah, so n, it doesn't really matter what you choose, but make sure whatever you choose is consistent. So if you're going with n minus 1, make sure it's always n minus 1. If you're going with n, make sure it's always n. But yeah, so if we run if you find, so if you find this degree centrality and sort it out by who's the most important, so node 51 is the one which met maybe 12% of the whole conference. So we can argue node 51 is an organizer, node 51 is a keynote speaker, node 51 is at the registration desk, because someone who's sitting at the registration desk will end up meeting a lot of people, and so it goes. And we will let's do this. No, let's not do this, but let's do the other bit. So now we'll be social scientists, and we'll try to infer things just by looking at a very nice picture. Is everyone ready for that? So, yep. So this picture was plotted with a lot of care. We put a lot of context into the picture itself, and on the right side you would see this changing of color, the matplotlib spectrum, and it starts right here, and it goes. It starts right here, and it goes in an anti-clockwise manner. So this, the color tells you the node. So this is node 1, this is node 2, this is node 3, and so on. You basically keep on going through this. And the black lines are basically the edges. And there's one information that I didn't mention, and that could maybe make a lot more sense in this context, is the node 1, node 2, these numbers were given by the time they walked into the conference. So if you come up at 8 a.m., you get the number 1. If you come up at 8:02, you get the number 2, and so on. So with this information, that this anti-clockwise is ordered according to time that they showed up, and the blacks are the edges between them, and we see a donut. Is there anything we can infer from this graph? Any ideas?
People didn't stay there very long.
All right, so one inference is that people did not stay there long. But we don't know anything about people did not stay long. It's just about who they talked to, or like who they were around.
Around people who came around the same time.
Yeah, so one thing that you could argue is that if the people came together, they stuck around. They didn't really talk to other people. So this is why this is to show you that visualization is very important. If, for example, if I did like nx draw.g, do you want to try that? It will actually take a bunch of time, but so yeah, anyone can. What can we infer from this? No, right? So that's why, like, I mean, to be fair, you can make this a bit pretty. You have ways of you can also like select some layouts. So if you do something like this, it will give you, and then you can also like make the nodes a bit smaller. So you can make this a bit pretty, which gives you a lot of context. But something like this is just, in my opinion, better. And because we kind of coded into a lot of context into the visualization itself, we can infer things like, people who stayed around, they kind of just stuck in their own circles, and that's why we see these very localized coils of edges. And if everyone was talking to each other, then we would not have this donut. And there's another thing that we can maybe try to find out with an arc plot. Let's plot it out. I mean, that same thing is also, we can also infer that same thing from here, but it's a bit harder to see here. Yeah, like someone had a question? Yeah.
Yes, what exactly does the color express in this diagram?
The Sokos plot.
No, but the color.
Yeah, the color bar is basically the node color, and the node color is it's telling you at what time they came in. So if the node color is 1, that's the first person that showed up. So this is the same plot, but on a straight line. And we basically see these communities that show up, these little dark blobs. So we can say that people kind of came into either at the same time, they stuck around and they didn't talk to each other, and so on. But yeah, so this was just one way of looking at importance, which is degree centrality. This is like the most basic one. There are much more fun ways, in my opinion. And for example, if you go back to the Twitter example of if you try to find who's the most important person on Twitter or any other network like this, and you come up with an answer, who has the most number of followers? That could be right, but nuance is missing from that. And the nuance bit is that, for example, let's say there's one Twitter user, or let's just not use Twitter. There's one, let's say we're in a transportation network. Yes, let's say we're in a transportation network. And we try to find which is the most important, let's say it's like a flight, it's like all the flights of all over the world, and we try to find which is the most important airport in the whole world. Any ideas what could that be? Which airport would be the most important airport in the whole world?
Many different definitions you could come up with.
Exactly. And so usually what you would come up with which has the most number of flights? So like London or Atlanta, New York, or Dubai or whatever. But one of the definitions that could help you understand that this, like what I'm trying to say better is that you also need to find airports which keep the world air network connected. For example, if there is an airport somewhere that flies to a bunch of other countries that no one else flies to. So let's say it's a spoiler, but let's just say it. So in Alaska, so like the main airport of Alaska has flights to every other airport in Alaska, but and the main airport is Anchorage. Like that has flights to every other airport in Alaska. But if you want to fly to mainland US, you can only fly from Anchorage. So if you're anywhere else, you need to fly first to Anchorage, and then you have to fly down. And if you do like a network analysis of the airport network, or like just the raw structure of the airport network in the US, you'll find that Anchorage is an extremely important airport. It's because of this, that it's holding the network together. This is just looking at the raw structure. This is not about number of flights. It's not about how big the airport is. It's just about if you care about the structure of the network. For example, if I'm the Minister of Transportation, I want to make sure my country or my region is connected. And if my region or country is not connected, that's a bad thing. So it's context. It's very important what you mean by importance and what you are trying to solve or what you are trying to figure out. But yeah, so we have 20 minutes left. But so there's another notebook in this thing. It's called structures, and here we try to find localized structures in a network. For example, triangles. So if I'm friends, let's say in Facebook, we have a very small friend circle, like 6 people. We all of us know each other, and if you look at the bigger Facebook network, you cannot infer anything about our friendship. But if you look at the localized structure, we have this complete graph, but all of us are friends with each other. So finding these localized structures in big graphs also tells you a lot of things. This apparently used to be used for LinkedIn, people you may know. So it was all about closing triangles. So if I'm connected with person A on LinkedIn and they are connected with person B, LinkedIn would come up with me oh, do you know person B? Because you're connected to A. So it could be used in recommendation algorithms. But yeah, so if you love what we are doing right now, then please feel free to go back and go through this notebook. And we're gonna jump to GraphBLAS now. Oops, where is? And by the way, this is I'm sorry, I don't think I showed you this. This is the whole thing. So right now, what we are doing is we went through section 1. We went through section 2, chapter 4, and there are a lot more chapters. And the spoiler was from the last chapter, which is where it's a case study of the airport network in the US. So if you have 8 hours on a weekend, you're bored, this is, you feel bad about binging something on Netflix, do this. So, but yeah, let's jump back. So, as I mentioned before, I love NetworkX, everything is perfect there, but it's slow in certain contexts. For example, if you're working with 10,000, 20,000 maximum, or 10 nodes, it's fine. Anything you're trying to increase the performance there, that's, in my opinion, is just over-engineering. But let's say you are a big business with lots and lots of data, with lots and lots of GPUs and lots of big multi-core CPUs. And the other thing is that NetworkX is not parallel. It's not parallel by design. So if it will only use a single core on your machine. It does dispatch, not dispatch, but it does use SciPy sparse in certain places. So you get the experience of multi-core, but for most of the cases, it's just normal pure Python. So it can get slow. So to fix this, last year, this is what we kind of came up with, is there are a bunch of faster libraries and ideas of how to speed up Python code, not Python, but speed up graph analytics code. So there was this another project called GraphBLAS, and we started working with them, like the team who made Python GraphBLAS, the Python bindings of GraphBLAS. GraphBLAS itself is like a specification of doing, it's a graph basic linear algebra system. It's a specification of doing graphs, as we saw in matrices, but with semi-rings. And I won't go into that, but let's just see how things can speed up. So the current idea is that we don't want to write any C, C++, CUDA, Fortran inside NetworkX, because it's very, very hard to maintain. And we want to make sure that NetworkX is installable in any device which can support CPython. And that's true. Like, NetworkX has no dependency by default. I mean, you can add new things if you want certain features, but for example, if you want plotting, you need to add matplotlib. But when you do pip install NetworkX, it just works. You don't, I mean, we build wheels, you don't even need to build wheels. But so that's by design. It's a pure Python library, we won't add CUDA in it. But how do we make it fast then, right? So the idea that we came up with is that we'll add something called dispatching. So things that people love about NetworkX, API. How to merge the love of API with performance, right? So here we have created like a random graph. It's called an Erdos-Renyi graph of 1,000 nodes, 0.5 like density. And we also create a GraphBLAS object by using this from NetworkX. So if you do type of G of B, it will give you, it's a graph. It looks like NetworkX. So for example, if we do type of G, it kind of follows the same thing. But these are inherently different objects. It's not a subclass. So what it does is that you can, I mean, if you have any specialized hardware and you work for a company that makes FPGAs or something, and they want to have a very specific backend for NetworkX, we can talk about that too. And so you have this class attribute. Again, like for people who are beginners in Python and this does not make any sense, it's fine. You don't need to worry about this. So there's a class attribute there, NetworkX plugin, which basically tells this GB is our GraphBLAS object. It tells you, like, this is a GraphBLAS object. Do something with it. So let's try. So if you look at this bit of code, it's not very scientific, but it is what I'm doing for benchmarking. Now, just timing that. So we call nx.pageRank. PageRank is an algorithm to find the importance of nodes. And PageRank is that billion-dollar algorithm because this is the one that kind of birthed Google. Page from Larry Page, web page, PageRank. So it's try to find, like, the initial idea was to find the most important link on the web. So like that is what PageRank was. So if we pass in a graph with 1,000 nodes, a dense graph with 1,000 nodes, it can calculate PageRank using just normal NetworkX with 300 milliseconds. Now, if you'll see that we are using the same API, like the only thing that we changed was what we are passing into PageRank. Like it's the same syntax. It becomes maybe like 6, 7, 8 times faster. So that's good. But no, when we are dealing in milliseconds, we don't really care about that speed up, right? Usually. So let's calculate something. It's called the betweenness centrality. So like if you remember, like the context centrality, the importance thing that I was talking about is this. Like betweenness centrality basically calculates the nodes which are very important to the network. In the case of the airport network and anchorage, because what it is running underneath is it takes 2 pairs of nodes, like basically like all the pairs of nodes in a graph, and it runs the shortest path between them. So you basically do it for all the pair of nodes in a graph. So NC2 basically, so you choose 2 nodes and basically find all the combinations that you can find, and then shortest path between them, and then you try to find a node through which most of these shortest paths go through. And if we go back to our example of anchorage, this is what was happening there, that if you want to find the shortest path between any airport in Alaska and, for example, any airport in the mainland US, you have to go through Anchorage. So it kept on coming up in the importance score. And see, I was giving this monologue because it takes a lot of time. So it took 57 seconds to run this on a 1,000-node network. Any guesses how fast we can do it in PageRank? In GraphBLAS? And again, like the idea behind that is that you don't have, the only thing that you need to change in your code base, for example, if you have a huge code base right now, you're using NetworkX, it's slow, you complain about it all the time. The only thing you need to change is this, and basically change your graph object that you're passing in. So if we just did this, like G equals, and the rest of your code is the same, it should work in theory. But any ideas how quick can we go with GraphBLAS? Any 10 times, 1,000 times, 20,000 times, any ideas? Just shout out the number. 100 times, all right. Are we ready? So if it's 100 times faster, it should be done in half a second, right? That's the number we are trying to hit. Are we ready? Whoopsie. See? Yeah, see? It was half a second, but we have an error. And what I wanted to show with this is that it's actually kind of hard to implement everything that is in NetworkX in a different, for example, in a different library or in a different backend. For example, if you're writing C code or in the context of GPUs, so we are also trying to make this work with GPUs. And by GPUs, it's basically using cuGraph. So cuGraph is something that comes out of NVIDIA's Rapids team. And they have their own, they basically try to follow NetworkX API, and they basically implemented the same thing for GPUs. And now we are working with them to make sure that the translation layer between going from Python API to GPUs is done through that. So for example, right now it's not possible, but in the future, what the idea would be that if you're a downstream library, for example, your graph machine learning library that uses NetworkX to do some things, you should just be able to set a config option in your, somewhere, and everything could be just moved to your GPU without you changing anything in your code base. It's not possible today. It would probably be not that easy just to change one line, but the idea is to make sure that lots of code that has been already written that should be able to speed up with just these config options. But yeah, coming back to the point that there's a very, very, very long tail of algorithms. I think there are more than 400 algorithms implemented in NetworkX right now, and it would be very hard to cover all of them in all the other backends. So right now we only have GraphBLAS, but soonish, maybe in the next month or so, we'll have a GPU backend too, backed by cuGraph. So, and it's very, very hard to make sure that they implement 400. They would not implement 400. You will not implement 400 algorithms in CUDA. So the idea would be that you use NetworkX where you don't have any other option. But for example, if you have a GPU, if you have a fast computer, you should be able to use your code and dispatch it to the fast bits. Dispatch to, for example, GPU if you have one, and if there's an algorithm for that. So that's the idea there. And how much time do you have? Yeah. So the idea is that you should be this is not really for, I think, end users, in the sense that if you know that NetworkX will be a bottleneck, then you can just go use GraphBLAS directly. You don't need to come to NetworkX. But for example, if you're building a library that builds on the abstraction of a graph rather than just NetworkX, if you're building, and you can use NetworkX as the abstraction layer, and that abstraction layer can either go to Python native dictionaries that we use, or GraphBLAS objects that Python GraphBLAS uses, or cuGraph for GPUs. And so this was supposed to be an exercise, and more not like code writing exercise, but more like an interactive exercise. Right now the problem is that, as you see, we need to basically keep two objects. One is a graph, the NetworkX object, which is, for example, the G. We have this one, and we have GraphBLAS. So in this case, whenever we hit for example, betweenness centrality is not implemented for GraphBLAS. Oh, in that case, we'll call graph. But this is again some logic that someone needs to implement downstream. Can we write our own new backend, which basically creates this meta graph that traps everything, and it just automatically chooses the best backend to dispatch to? And the good part about this is that if you have an idea, please talk to me, because we have not implemented this yet. And for us, we're just experimenting it with it, and the idea is just to can we make something like this code? The idea is can this code pass? So we create a NetworkX graph, we create a GraphBLAS object, and then we create a new graph. It's called G, and we can just pass this G around, because most of the people, most of the downstream libraries, what they would have in their code bases would be something like this. Just these calls. They would not need to worry about changing changing data, and because that's a very expensive operation. So for example, if you had a code where you read in a NetworkX object from a CSV file, you convert it to a GraphBLAS object, and then you run something, 99% of the time would be spent in the conversion step. So data conversion is expensive. So if we can basically store pointers to all of these different, which is again not so efficient, right? But if we can store pointers to a GraphBLAS object, something on the GPU memory. So if we can keep a pointer into this meta graph, and meta wrap. Meta graph is another library, but meta wrap. Can we design something like this? And the idea was can we make something like this work? And it works. I made something, but so both of these things work. And in this case, what it does is that it will dispatch PageRank to GraphBLAS, because we know it's faster. Let's just assume it's faster. And in this context, because it's not implemented by GraphBLAS, it will be dispatched to NetworkX. This is not an easy problem, but this is a okay problem. What happens if we add a new backend? So for example, if we add a backend which implements all of these graph algorithms in parallel on a multi-cluster CPU nodes, how do we select these heuristics of a way to throw our code to? So if you have any ideas, I don't think shouting out would be convenient, but please feel free to catch me, and let's have a talk. But yeah, so this was the tutorial. I know I have a feeling I went too fast, but sorry about that. But I wanted to cover a bunch of stuff. But if you feel like you love what you saw today, please go to this website. We have everything is a Jupyter. On the website it's not Jupyter Notebook, but everything is available in this thing. And Eric Ma, the other person who also worked on this Jupyter book with me, he has also put videos up there, so you can also do things there. And yeah, so if you have any questions, please let me know. If not, thank you.
Was that GraphBLAS Jupyter Notebook available somewhere?
I can put that up if you want. Yeah, I'll push it somewhere, and I can share you a link. But that's supposed to go in it's supposed to go in NX guides. Oops, I don't have internet, but it will be up there. Yeah.
Is there a way to visualize the graphs of hundreds of nodes in a way that it's actually readable and not just a ball of fur?
I mean, I think it's important to the layout is the most important bit, right? If you can find a layout that works for you, I mean, then there are these force-directed graphs, right? That it will give you a nice layout, but it's hard. I mean, you can, it's hard.
Hello. Does NetworkX apply some combinatorial optimization solutions to some problems? Like, for example, does it use any solver to give? No, okay.
No, it's not using any solver. It's just basic combinatorial for loops and things like that.
No. Like, for example, to provide some solution to a TSP-like problem.
Oh yeah, it does. So there's a approximate solution for TSP, but we actually just a couple of weeks back I actually ran into one of the developers of CVXPy, and they told us that they have a very nice 4-line solution for TSP with their convex optimization toolkit. We don't implement that, but there are things out there that does, and we have our own heuristic implementation of approximation.
Okay, nice. Okay, thank you.
All right. Well, then have a fun conference. Thanks for showing up on a Monday morning for this, and I hope you had fun.